Hi everyone, and welcome back to my video series on making a tap wrench. In this video we're going to be tackling the handles for the tap wrench, and in doing so we're going to use the kind of techniques that you're going to use on most lathe parts. So a mastery of these techniques will mean that you can make pretty much any part on the lathe. Now as far as lathe techniques go, it doesn't get much more basic than facing, which is cutting on the end of the part. On the vast majority of parts that you're going to make on the lathe, you're going to start off by facing one side, then turning the part around and facing the other end so you can get a measurement and find out where you are. Facing cuts will show you very quickly whether your tool is on center or not, because you'll end up with a little nib in the middle of your part if it's not. If your tool is too low and it passes below the center line of the part, you'll end up with a cylindrical nib, whereas you'll end up with a conical one if you pass above the center line. Now that my cut is done, I'm going to quickly deburr the edge of the part with the file, and then I'm going to turn it around and do the same thing to the other end. I would normally try to have this sticking out far enough that I can actually get my measurement while it's in the lathe, but that's not really possible on this because the blank is just too long. That means I'm going to have to take this part out of the lathe after this cut, and then take a measurement, put it back in, touch off on that surface, and then I'll be able to cut it down to final length. While we're waiting for this cut to finish, I'd really like to poll the audience a little bit about my voiceover. It's a lot faster for me to shoot these videos when I'm not having to machine and think about what I'm trying to say at the same time, so it just takes a lot fewer takes. But what do you guys think? Is it more clear? Is it less clear? Is it about the same? Let me know down in the comments. I really appreciate your input. I've got a 6 to 7 inch micrometer here because my blank is 6 1/8 inches long. This is a little tough to juggle with one hand. I would normally actually put this on the headstock or something like that and measure it that way. That way I could hold the micrometer with two hands, but then it would be off camera and that kind of defeats the point of a video. Now that I've established what my length of the part is, I know exactly how much I need to remove. So I'm going to put it back in the chuck, I'm going to touch off as gently as I possibly can on the end of the piece, and then I'm going to remove that material. Here's one final measurement on my part to make sure that I'm within my tolerance. And make sure when you're measuring anything, whether it's round stock or square stock, that you give it a little bit of a twist on the micrometer to make sure the micrometer anvils are seated on the part. Otherwise your measurement could go a little bit awry. Now I can put my part back in, and I need to make sure that it's sticking out far enough from the chuck to machine the feature, and so that I won't run into the chuck with my tool or my tool holder. A quick double check never hurt anybody. Since I took my part out of the chuck, I need to make sure that I touch off on the end to establish my z-axis location, and I need to do the same on the diameter. Then I'm going to take a first pass so I can get a good solid measurement on where I actually am. That first cut was a depth of cut of 20 thousandths of an inch, which is also the same depth of cut that I use for my finish passes. I use this depth of cut because it takes a consistent amount off and leaves a good surface finish, which is very important. Now that I have my measurement, I know exactly where the tip of my tool is, and that means I know exactly how far I need to go to get to my target dimension. This is my first 20 thousandths finishing pass after all of the roughing cuts that I've made. I do this because I'm going to need to make a measurement after it, and I want to make sure it's a consistent depth of cut. I also made a facing cut at the end of my last pass, and now I'm taking the burr off of the end of the piece so I can get a measurement with a pair of calipers on the length of this step. Now it's time to get a measurement on the diameter so that I know how much to take off on my last pass. Now I'm just getting my measurement on the length of that step with a pair of calipers, using the end of the jaws. If you haven't seen my video on the 4 ways of measuring with a pair of calipers, check that out. I'll put a link to it down in the description. Here's my last pass on the main body of this. The dimension is listed on the print as being 375 plus nothing minus 2, so I'm actually aiming for 374 thousandths of an inch. This will give me plenty of clearance with the jaws. Now it's time for one last measurement just to verify that I hit my target. That last pass not only got down to the diameter, but I also finished machining the length of that step as well, based on my caliper measurement from before. This pass is strictly on the threaded portion of this feature, and it's just to ensure that there's enough clearance on the thread and that they conform to the specifications for the thread. Of course, we also have to confirm that we meet our specifications on this, and the only way to do that is with a measurement. Here I'm just using a tool that I ground to cut the chamfers. It's a 90-degree point, so 45 degrees on either side of center. Now I'm switching to a tool that I ground for cutting the thread relief. It's going to give me the width of my relief as well as the chamfer on the end of the threads. This is a form tool, so you need to slow your RPM down a little bit because of all of the surface area of the tool in contact with the part. You're also going to need to go ahead and touch off on the end so that you know exactly how far in to move. In this case, on the print, it shows that the square end of the thread relief is 0.6875 from the end. I've touched off on the diameter and input that number into my digital readout so I can stop before I reach my target dimension. This is going to allow me to get a measurement at the bottom of the thread relief with a pair of calipers to ensure that I get the correct dimension. Now I just need to move in the remaining distance. I'd also like to point out that I've been using a fair amount of oil the entire time that I've been making this cut. That's generally a very good idea when you're working with form tools. Once the thread relief is cut, make sure to deburr the square shoulder, otherwise the fit with the jaws will be affected. Now it's time to load up my threading tool. Notice that the point is offset slightly to the left. That's so I can get closer to the shoulder without running into it. The first order of business when you're setting up a threading tool is to make sure the tool is actually perpendicular to the work. In this case, I put my print underneath it, and I put the lamp as low as I can possibly go so that I can see the silhouette. Then I can use my center gauge to determine whether I'm perpendicular to the part. The gauge is held firmly against the diameter of the part to make sure that it's square. It may not show up very well on camera, but with the silhouette you can see very clearly if there's any light between the gauge and the tip of your tool. You just need to adjust the angle of your tool post until you don't see any light between the tip of your tool and the center gauge. I'll take this time to point out that this is actually the second of the 2 handles. I went ahead and did this shot from above so it would be a little bit clearer. Once you're satisfied that the tool is nice and square, you just need to touch off on the diameter, and I'm going to zero my dial as well as my digital readout. There's no one right way to cut a thread. You can feed straight in, but I tend not to do that because you end up with 2 chips coming in from each side and colliding in the middle, which can leave a bad surface finish in harder materials like steel. I like to angle my compound. You want the compound angled at half the angle of the thread, and what that angle is depends on where 0 is on your compound scale. Different lathes have it in different places. A lot of older lathes have 0 over here, which puts the compound perpendicular to the lathe axis in that position. A lot of newer lathes, such as this one, have 0 over here, which puts the compound parallel to the lathe axis instead. In this case, the angle that I need is 60½ degrees. If the 0 is over here, you would need to have the textbook answer, which is 29½ degrees. You'll need to find the threading chart on your lathe and find 16 threads per inch for this. So in this case, I need to be in E1 on my handles. For my students out at Parkland, here's your E handle, and this is the handle that needs to be in the position 1. You'll also have to make sure that the lower 3 handles on the gearbox are all in the TPI position, threads per inch, and you'll almost certainly have to move the chuck in order to get them to mesh into gear. Now these controls are going to be different for every machine out there. Different brands have different ways of engaging threading. So for the viewers at home, you just have to figure out how do I get the right threads per inch and how do I engage the lead screw. This is the half nut lever on the machine, and most lathes seem to have it right around the same area, but it's literally 2 halves of a nut that close around the lead screw of the machine, and that is what drives the carriage for threading. Somewhere on every lathe is a chart that says where you can engage the half nuts at the threading dial position. And in this case, we have an even numbered thread, so we can engage it at any dial position. This is your threading dial. This is what allows you to engage the half nuts to the lead screw so that you can cut your threads and follow the thread that was previously cut. Otherwise, you would end up crossing those threads and destroy all your progress. This is a scratch pass so that I can verify my threads per inch to make sure that I actually have the gearing set correctly. The center gauge has a number of scales on the end, so you can find one that matches your threads per inch, in this case 32, and I should have a thread at every second mark. Now that I know my gearing is set correctly, it's just a matter of repeating the process over and over until the thread is to the correct depth. After each pass, I return back to the beginning of the thread. I bring my crossfeed dial back into 0, which I verify on the digital readout. I feed in with my compound, and then I engage the half nuts as soon as I reach a handy number on the threading dial. In this case, I have a thread relief at the end of the thread, but if you didn't have that, you need to make sure that you get in the habit of pulling out on the crossfeed before you disengage the half nuts. Otherwise, you could break the tip of your tool, and of course you'll cut a thread relief when you don't want one. Here we are zoomed in on the action. Again, I'm feeding in with my compound. I've brought my crossfeed back to 0. I'll put a little bit more oil on there, it never hurts. Then I wait for a number to come up on the threading dial and engage my half nuts. At the end of the cut, pull out on the crossfeed, disengage, and then you can return to the beginning. When you look up thread specifications in either Machinery's Handbook or online, you'll find 3 dimensions that are given. You'll have major diameter, minor diameter, and pitch diameter. I've put those up on my screen so that you can see those and have them as a reference, and also to distract you from how blurry the shot is getting. The thread is called out as a 3/8 16 UNC 2A. So 3/8 is your nominal major diameter, 16 is the number of threads per inch, UN is Unified National, C means it's the coarse thread in that series, which is the 16 threads per inch, 2 is the class of fit, and we'll get to that in a second, and then A means it's an external thread. It could say B, which would be an internal thread. Since this is an external thread, we have a range for the major diameter and a single number for the minor diameter, which would be the smallest diameter of the thread. If this was 2B instead, then you would have a single number for major diameter and a range for the minor diameter. The pitch diameter is actually what determines your class of fit. Class 1 would actually be the loosest fit. Class 2 is sort of like your average everyday nut and bolt that you would get at the hardware store, and Class 3 would be your tightest. Whenever a thread is called out on a print, you would look up these specifications for whatever thread that is, and you would turn down your major diameter to somewhere within that range, just like any other tolerance. Your minor diameter would be there to tell you how deep to make your thread relief or the chamfer at the beginning of the thread. And then your pitch diameter you would measure with a thread mic to make sure that you actually fit your class specification. I'm going to put some top-down shots here from the second handle just so you can see threading a little bit clearer. And hopefully this will clear up any confusion as to what's happening. We're in the cut and you can see me right here pulling out and disengaging the half nut, so I'm no longer advancing towards the chuck. I bring it back into 0, and at the next opportunity I'll re-engage the half nuts and cut the next thread. I should also take the time to point out that with each successive cut, you're going to be taking more and more material off, and you'll have more of the tool in contact with the work. This means that each successive cut will have to be a little bit shallower than the last one in order to prevent chatter or tearing of the threads. Because of this, your first cut might be 0.010 of an inch deep, but your last cut might only be 1 or 0.002 of an inch deep. I've skipped forward a bit to show the measuring with a thread micrometer. A thread micrometer has one anvil that's V-shaped and another anvil that's pointed. The V anvil goes on top of the crest of one side and the pointed anvil goes in between threads on the opposite side, and this measures pitch diameter directly. This fact is one big advantage for thread micrometers, but there are some disadvantages as well. For one thing, they can be very difficult to center on the threads and get a good measurement. And the type that this one is, with interchangeable anvils, is prohibitively expensive. Those anvils would be changed out depending on what thread you're cutting, so a finer thread would need a different set of anvils than a very coarse thread. Thread micrometers with fixed anvils are available, and they're considerably cheaper, and generally pretty available on the used market. Your threads will not have a sharp point. They should have a bit of a flat on them, so you should start measuring them before they get to that point. Otherwise, you'll almost certainly be too small on your pitch diameter. It's also a good practice to take a spring pass or a cleanup pass without adjusting the compound before you do your measurements. So you would just bring the crossfeed back to 0, don't touch the compound at all, and it usually takes a small chip and produces a better surface finish. Your pitch diameter range isn't quite like other tolerances where you should aim for the middle. You should stop as soon as you're somewhere within that range. The reason for this is that it's exceedingly easy to hop over that range, even with just 1/1000th of an inch cut, because you're opening up that V, which changes the measurement dramatically. It always seems to take off more than you think it will. Some of you might be asking, why the heck are you single point threading this? Why not use a die? And the answer is that dies rarely ever start perfectly straight. They'll always be slightly angled, and especially if you've got a very long thread that you're cutting, you end up cutting more on one side than the other, so you'll have very deep threads on one side and practically non-existent threads on the other. It's called drunk threads. With single point threading, you are guaranteed to have threads that are not only concentric to the axis of the part, but also square to it. Another way of measuring threads is with a thread wire set like this. They come in various sizes, each with 3 pins. On the inside of your thread wire set, you'll find a chart. You find the threads per inch that you're cutting, and next to that it will tell you what size wires to use, and then a couple of spots over is a column called the constant. The constant is the number that you subtract from the measurement that you get over the wires. You'll have 2 wires on one side and 1 on the other, and you use a regular micrometer to measure over the tops of the wires. Subtracting the constant from your measurement gives you the pitch diameter of the thread. What I do is take my constant and add it to both numbers in my pitch diameter range, and that gives me a measurement over the wires, which I'll put on the screen. Doing it this way means I don't have to break out a calculator every single time I measure. I simply cut until my measurement over the wires is somewhere within that range, just like I would with the pitch diameter. Juggling the wires without dropping them in the chip pan is a bit of a problem, so I put a little dab of grease there and it holds the two wires on the top. Then I'm free to hold the wire below. The grease won't affect the measurement in any appreciable way, and it keeps you from dropping the pins and having to search for them. The big advantage to this system is cost. A set of thread wires might cost you $20 to $25, and you use them with the outside micrometers that you already have. The wire size and the constant would be the same if it was 3/8 16 like in this case, or if it was 30 inches 16. This makes it an incredibly cost-effective way of measuring threads. To prepare for the knurling, we're going to need to center drill the end of the piece. It's going to need to be supported at the end by the live center because we're going to have quite a lot of material sticking out, and the knurling is very strenuous on the piece, to say the least. If it was left unsupported, it would almost certainly flex away and you would probably not get a very good knurled pattern on the piece. When center drilling, I go about halfway to 2/3 of the way up the tapered portion of the center drill. You do not want to get into the larger cylindrical portion of the center drill. That won't allow the center to seat inside the part. The tool I'm going to use for the knurl is a scissor knurler, and this takes a lot of the pressure off of the machine and instead transfers it to the screw in the back. You use the screw to adjust the size in between the rolls, and you can actually change out the rolls to different types. This allows you to use coarse, medium, or fine diamond knurls, different straight knurls, all sorts of stuff. You can see the tool pivots on the part that's held in the tool post, so it's largely self-centering, but it's still a good idea to actually get it pretty well centered on the machine. I've got a lot of extra material sticking out from the machine, and that's for a couple of reasons. For one thing, I need to set the knurls so that I get the right pattern, and I'm going to do that in the waist area of this handle, the part that's going to be turned away later. My basic technique is to start forward of center, and then I tighten up the nut to where I'm getting a little bit of contact with the part. Then I can finish it off by feeding inwards with the cross feed. When you're doing this setup, you really want to make sure that you're doing it on a piece of stock that's the exact same size as the part you're going to be knurling. It's very common to get one wheel or both wheels doubling up where you get twice the pattern that you're expecting, and that doesn't look very good. The pattern of your knurl can be adjusted by changing the depth on your cross feed. Doing this on a piece of scrap material or in the waist area of your part like we're doing here allows you to play around a bit to get the pattern and the depth of the pattern that you're looking for. I actually got incredibly lucky on my first try and got the pattern that I was looking for. So this is actually footage of the second handle, and I purposely went too light the first time and I got a pattern that doubled up on both wheels. I tried again and I went just a little bit deeper on the cross feed, and this time I got a pattern that was good on one of the wheels but doubled up on the second one, so I had twice as many marks in one direction as I did in the other. This is a much more typical situation. You'll have to move over to a fresh area so that it doesn't just follow the pattern that's already been screwed up, and you keep changing your depth until you get the pattern or the sharpness of the knurl that you want. There are a lot of people out there who I think overthink knurling. They make it a process that's much more complicated than it needs to be. You hear them talking about figuring out the diameter of the piece, the correct diameter for the pitch of the knurl, and in practice that really doesn't seem to be necessary. You can just keep changing your depth until you get the pattern that you want. It accomplishes the exact same thing, it's just in a much less scientific way. Moreover, you get the pattern that you want without having to do a bunch of extra work in turning down the stock to a certain diameter. Once you get the pattern that you're looking for, you zero your dial or your digital readout, or better yet both, and that way you're ensuring that you get a consistent depth of the knurl between parts. I highly recommend doing the knurling on both parts at the same time. Here we are back on our first handle, which is a bit of a clearer shot, and we're going to do this knurl. I reversed the feed direction on the machine, so I'm feeding from the headstock towards the tailstock. That makes it a little bit more rigid. I'm also constantly flooding it with oil and switching between the two wheels. Knurling is a displacing operation rather than a cutting one, but you are actually producing some tiny little chips as they get kind of torn away from the surface. The constant flood of oil flushes those chips out and makes the surface look a little bit better, a little cleaner, and it also lubricates the knurling wheels. The finished length of the knurl is 2 inches from the end of the piece, so I started a little bit early in the waist area to make sure that at the beginning of that 2 inches I've got the full pattern and not a partial pattern, which can sometimes happen. I also keep feeding until the knurling wheels are about halfway off the part, and then I stop. This ensures that I get the full pattern all the way to the end of the piece. To do the undercuts on the handle, I've switched it over to a collet setup on one of our other lathes here. This is going to allow me to grip onto the threaded portion without damaging my threads. I've scribed a line on this end where the cut should end, and I've set up a dial indicator that bears against the chip guard. I just have to align my tool with the scribed line, and then I'll set my dial indicator at 0, and I've done basically the same thing on the other end. I've marked it with a Sharpie, and machining up to that mark will leave me plenty of extra room to get the finished length of that cut. This allows me to bring my tool up to that mark, and I'll set another indicator on the ways so that I can set that side to 0 as well. Once I'm satisfied with the placement of my indicators, I'll go ahead and touch off and take a token cut just so I can get a measurement and see where I am. From here on out, it's a pretty straightforward turning operation. I'm using the same 45-degree chamfering tool that I used earlier in the project to cut the chamfer at the beginning of the thread. This is going to give me the same 45-degree chamfer at the end of the knurl and at the end of that shoulder. I did put a slight radius on the tip of that chamfering tool to ensure a good surface finish on this operation. To get a measurement on the length of this cut, I used the inside jaws on a pair of calipers and just went from corner to corner at the bottom of those two chamfers. That's not terribly exact, but this is far from a critical dimension. It's strictly aesthetic. Once I have that measurement, then I can move accordingly using the dial indicator on the knurled end of the cut. I took this measurement before my last finish pass so that I could make sure that I got my final diameter and my final length at the exact same time. This gives me a consistent surface finish. I figured I would close out this video by showing what I had to do in order to get these overhead shots for the threading. I couldn't get the shot with a tripod, it just couldn't get the right angle, plus it was in the way and it was getting bumped by the machinery handles. So I clamped a piece of aluminum onto our die cart, and then I clamped a piece of 1/4-20 threaded rod on there that's screwed into the bottom of my camera. Just a few zip ties later and I could wheel it right over the chuck and get a fantastic shot just for you guys. I hope you found this video helpful, and if you did, please consider hitting the like and subscribe buttons down below, and leave me a comment if you have any questions. Thanks for watching. I'll see you next time.